It's now time to actually do some Taylor expansions. Okay, we saw the definition in the last video, how to construct it, and now what better way to understand how they work, okay, than to actually play with them. So we're going to go ahead and take some functions. We're going to create some Taylor expansions. Okay, so let's take a look at this one here. We want to find a Taylor series for e to the x centered around a equals 2. So let's go ahead and remind ourselves what the definition of the Taylor expansion is. Okay, so the Taylor expansion, which I'll put in this box here, if I want to expand f of x near a, we'll need the following. It's an infinite sum from n equals 0 to infinity of, remember, we'll have the nth derivative evaluated at our center point a, divided by n factorial. Those are the Taylor coefficients. And we're going to need powers of x minus a, so we need x minus a to the n. That is our Taylor expansion. Okay, so what do we need to do? We need to first find some derivatives. Okay, let's go ahead and try to see if we can find the pattern here. So our function here, f of x, is e to the x. And thankfully, e to the x has its own derivative. So if we see here, if we take derivatives here, the first derivative is e to the x, the second derivative is e to the x, the third derivative is e to the x, and we have an easy pattern here because it's just an exponential. So what's the nth derivative of e to the x? Well, surprise, surprise, it's just e to the x. Okay? So the nth derivative of e to the x is just e to the x. That's so easy, right? Okay, that's the first step. We need to figure out what the derivatives are and see if we have a pattern, and indeed we do here. Okay, now we're going to go ahead and evaluate these at our center point. Okay, so we're going to go ahead and evaluate at our center point. So we have f of 2, that's just e squared, whatever that number is, something like 7, I think. Okay, the first derivative at 2, well, again, the derivative of e to the x is itself, so e squared again comes out. All these values are e squared. All those values are e squared. Okay, so we already have a nice pattern here for our Taylor expansion. Okay, so we took the derivatives, then we evaluated them. What's next? We're going to go ahead and scale by the factorials, okay? So our general term, we can just go ahead and write it here. Our general term, okay, the nth derivative at 2 over n factorial, okay, well, it's just e squared over n factorial. All right? And so how do we write the Taylor expansion for this one? Okay, so we have e to the x near x equals 2 can be represented as follows. The infinite sum from n equals 0 to infinity of, so let's look at our Taylor coefficients, e squared over n factorial. Those are our Taylor coefficients. And then we're going to expand around x minus 2. So we have x minus 2 to the nth power. And that's your Taylor expansion. That's all you need to do. That is all you need to do. Okay, so it works out pretty well, right? You find the derivatives, see if you can find the pattern, evaluate the derivatives at your center point. Here, in this case, that center point is a equals 2. And now you get the general term and combine all that into a nice, tidy, infinite sum. So that just works out extremely nicely, does it not? Okay, well, let's go ahead and look at our next one here. 1 over x, this time centered at a equals 1. Now, if you remember, we did this one way by exploiting the geometric series trick. And in fact, you can still do that here. But let's go ahead and do this with the Taylor approximation. So again, the first thing is we're going to need to look at our function and all of its derivatives. Okay, so we're going to need to try to find a pattern. So f of x here is 1 over x. Okay, now the first derivative here, if we use the power rule here, so x to the minus 1, okay, we'll take the derivative of that. We get minus x to the minus 2, so that's minus 1 over x squared. The second derivative there, okay, the minus signs will drop, okay, because minus times minus is plus, okay. But then I'll have a 2 in the numerator times x cubed. Again, this is just power rule. The third derivative, okay, we'll get another negative sign. Then 2 times 3, that's a 6 over x to the fourth. And let's do one more just for good measure here. Okay, for good measure, we have the fourth derivative of x, of f of x. We'll get negative 4 times 6, which is 24, divided by x to the fifth. And you know what, just if you haven't seen the pattern yet, let's go one more time here. The fifth derivative would actually end up being minus 120 over x to the sixth. Now, I want you to take a look at these numbers that I'm going to be highlighting here in orange. Okay, we have 1, 1, 2, 6, 24, 120. Now, I want you to think about the patterns that are arising here, right? When we do the power rule, okay, we'll have x to the minus 1, then minus 1 times x to the minus 2, minus 2 times minus 1 times x to the minus 3, then we get minus 1 times minus 2 times minus 3. What's really happening there aside from the minus signs? Well, we're getting factorials out of this. So we conjecture, and we can actually show this, if we continue this pattern, we will get that the nth derivative of this guy, the nth derivative of 1 over x, is n factorial divided by x to the n plus 1, okay? But then it alternates, okay? So the odd number derivatives get a minus, the even numbers get a plus. So we have minus 1 to the n. And that is our general form. That's our general form for the derivative. Okay? So we got the first part down. Now let's go ahead and evaluate these derivatives at our center point, which is a equals 1. So if we do that here, f of 1 is just, well, 1. Okay, f prime at 1 is equal to minus 1. F double prime at 1. Okay, we get a 2. The third derivative, we get a minus 6. The fourth derivative, we get a 24, and so on. So in general, our nth derivative at 1, okay, will be minus 1 to the n times n factorial divided by 1 to the n plus 1, but 1's any integer power is just 1, so we have minus 1 to the n times n factorial. Okay, so now we have the values of the derivatives. Now we're just going to go ahead and divide each of these by n factorial. And in fact, when we do that here, okay, when we do the nth derivative at 1 divided by n factorial, well, I already have an n factorial on the right-hand side there. So the nth derivative is just minus 1 to the n. And now I can glue everything together. So we have our Taylor expansion, okay? If I want to write this as an infinite sum, 1 over x can be approximated with, okay, near a equals 1. We'll have this infinite sum. Okay, then our Taylor coefficients, which in this case is just minus 1 to the n, times x minus 1 raised to the nth power. That's all it is. Okay, if you wanted to write out the actual polynomial that results, you just take these coefficients and go ahead and write them out. So let's just do that here for kicks. Okay, so we'll get 1 minus x minus 1. Then we have plus, let's see here, 2 times x minus 1 squared minus 6 times x minus 1 cubed. Okay, plus 24 x minus 1 to the fourth power, and so on. That's it. Okay, so we now see how to write this as an infinite sum. We now also see how to do this just writing out the actual terms. So let's keep moving on here. Let's do this one, sine of x near pi over 2. Okay, this one's going to be very interesting, so I'm going to need plenty of room. Okay, so let's go ahead and go through our usual routine here. We're going to first start by taking derivatives. So derivative of sine is cosine. So let's just first write down here sine of x. Okay, then f prime. Okay, the derivative is cosine of x. Okay, then the second derivative is negative sine of x. Okay, and the next derivative here, the third derivative is minus cosine. And then you see that this pattern repeats, right? Okay, so let's go ahead and just write, I'm going to go ahead and write down a few of these derivatives and we'll come back. And we're back. Just wanted to go ahead and write these derivatives down so you didn't have to go through seeing me struggle with some of this. So notice here that we have our usual derivative tree for sines and cosines, right? Sine, cosine, minus cosine, and then it cycles back. All right, but now there's not really an immediate pattern that arises here, but once we plug in this number, our center point, we see something magical happen. So if we want to evaluate this, okay, f at pi over 2, So what is the sine of pi over 2? Think back to your unit circle. Sine of pi over 2 is 1. Okay, now the derivative at pi over 2. Cosine of pi over 2 is 0. Okay, the second derivative at pi over 2, well, again, sine of pi over 2 is 1, so the second derivative there is minus 1. And the third derivative, okay, the third derivative at pi over 2 is 0. And so you're going to see this interesting thing happen here. Only the even numbered terms, okay, contribute anything to the sum here, as the odd numbered terms, all the odd numbered derivatives, give us a 0. So that's pretty powerful, okay? So the only things that matter here, okay, let's go ahead and make a note here, okay? Only even numbered terms contribute. So only the even numbered terms contribute to the sum. Okay, so we're going to go ahead and do a bit of clever relabeling here because I don't need the odd numbered terms here. And so here's what I'm going to do. I'm going to go ahead and put this in this light blue here. So if I take the derivative of this function, and it's an even numbered derivative, so this is going to be the 2kth derivative, say. Okay, remember that an even number is 2 times an integer. Okay, and I evaluate this at pi over 2. Okay, well, I'm still alternating it, a plus minus pattern. Okay, so when k is equal to 0, the 0th derivative is just a function value. So when k is equal to 0, we get a 1. K is equal to 1, the second derivative is a minus. Okay, so odd numbered k's will go ahead and get the alternating bit, minus 1 to the k. And finally, okay, what do I get here? Well, there's really nothing else to say, right? Because I'm just multiplying by 1. So the derivative, the 2kth derivative, at these even numbered points, okay, depends on the value of k, and we just cycle plus minus plus minus. And then we do our usual thing, we just go ahead and scale, but now this time, because we only have the even numbered terms, okay, because we have the even numbered terms, we have to be very careful here. We have the even numbered terms, going to go ahead and scale by the appropriate factorial. Okay, so we're just taking here n equals 2k in this case. Okay, because those are the only terms in the sum that contribute. So the 2kth derivative at pi over 2 divided by the factorial of 2k is just minus 1 to the k over 2k factorial. All right, and so our approximation for sine of x near a equals pi over 2 is as follows. It's an infinite sum, okay, from n equals 0 to infinity. Probably should have put an n there, but that's fine. Okay, what are our Taylor coefficients here? Well, our Taylor coefficients are just minus 1 to the n over 2n factorial, just from what we have down below here. Okay, this goes up there. Okay, because those are our Taylor coefficients. And now what about our powers of x? We'll have x minus pi over 2, x minus pi over 2 raised to which power? Well, again, we're only counting the even number terms because the odd number terms don't contribute anything. They're 0. This is that thing to 2n. And that is our expansion for sine of x. Now, bonus points. What function is this really? See if you can figure that out with using your trig identities. What is the sine of x minus pi over 2? Hint, hint, hint. All right. Now, let's go ahead and take a look at 2 last examples here, some Maclaurin expansions. Now, remember the Maclaurin expansion, okay, for the Maclaurin expansion, we're going to take a equals 0. Okay, the Maclaurin series is a Taylor series centered at 0. So we're evaluating these derivatives at 0. So nothing changes, we're just evaluating these derivatives at 0. Now, we've already done e to the x, okay, but I want to go ahead and demonstrate something here. Okay, you can always generate these series, okay, if you don't remember the base form. This guy that we're looking at here almost looks like just our e to the x. We already expanded an e to the something already. Here expanded e to the u around a certain point, but now we're going to do this around 0. But watch the magic happen. So let's go ahead and do our usual process here. Okay, f of x is e to the 3x. What's our derivative? Okay, exponentials are still their own derivative, but here, because we have another function inside the exponent, chain rule, so a 3 comes down. 3e to 3x. The second derivative, we get another 3. That's 9. The third derivative will give us a 27 coefficient. Okay. The fourth derivative, we'll get another 3. 27 times 3 is 81. But what's the pattern? Okay, we're still going to get an e to the 3x, okay, but now we're multiplying by a power of 3, okay? So the nth derivative here at x is 3 to the n times e to the 3x, okay? E to the n times 3 to the n times e to the 3x. That's a lot of weird sounds that sound the same. Now we're going to go ahead and evaluate these at 0, because again, we have a Maclaurin expansion, so we're going to go ahead and evaluate these at 0. Well, e to the 0 is 1, so that means all that remains here is just all these magical multipliers to come out of there. So the derivative at 0 will just be 3, because 3 times e to the 0, that's 3. The second derivative, we get a 9. The third derivative, we get a 27. The fourth gives us an 81. I don't know why I did that. Okay, because that's too clunky here. The fourth derivative at 0 is 81. The fifth would give you 243, and so on. So the nth derivative at 0 is just 3 to the n. Now, how do we get our Taylor coefficients again once we found our general pattern for the fn's, for the derivatives at the point? We just go ahead and divide by n factorial. So our Taylor coefficients, or if you want, the Maclaurin coefficients here, the nth derivative at 0 over n factorial, that's just 3 to the n over n factorial. And now we get this beautiful expansion, one of my favorite expansions here. E to the 3x is expanded as follows. We're summing from n equals 0 to infinity. And then we'll have our Taylor coefficients, 3 to the n over n factorial. And then we're going to multiply that by x to the n, because we're centering around 0. And that's it. That's all you got to do. Okay, same process. Just because it's a Maclaurin series, nothing changes. Okay. Now, I want to remark here, we've already expanded e to the u here, okay, in the first problem, which I'll go back to real quick. In the first problem, we expanded an e to the x type thing, okay, but that was around 2, and we got a similar looking expansion, right? We got a similar expansion, except now we had an e squared floating around there. Now, another way that you can do this is as follows. If you know to expand e to the something near 0 as the following, okay, you have x to the n over n factorial. Well, in this case, it's a u. Okay. If you know how to expand that, then just like we did in making new power series from old, you can replace that u or x or whatever with a brand new object. And so in this case, what you can also do is replace the u there with a 3x. And you'll still get the same expansion. I encourage you to try that out for yourself. All right. Now, let's take a look at this one, the Maclaurin expansion for x cubed sine x. Now, this is again demonstrating this whole new power series from old, okay? I'm multiplying by a power of x already, and I don't want to take derivatives of this thing because I'm going to have to use the product rule multiple times, and that just gets a little annoying. So what we're going to do instead is this. We're going to go ahead and expand instead. We're going to expand this helper function. Okay, we have a helper function here. I'm going to call g of x equals sine of x, and so that f of x is equal to x cubed times g of x. Now, if I know how to expand g, I know how to expand f, because ultimately in the sum, I'm going to have an x cubed out front multiplying the sum, and I can just push that in. So all my powers of x will get pushed up by 3. Spoiler alert. What do I really mean? Well, we already expanded sine of x. Let's remind you here. Okay. Remember that, well, we expanded a variant of sine. So I guess we should just go ahead and write this down here. So f of x is sine x. The derivative is the cosine. I'm only going to write down the first 4 derivatives. Okay. 1, 2, 3. So we have minus cosine. And then the fourth derivative is just sine of x. Okay. Now, let's think about this. We want to evaluate this at 0. Well, sine of 0 is 0, and the cosine of 0 is 1. And again, the sine of 0 is 0, the cosine of 0 is 1, but we have a minus, so that's a minus 1. So just like we had with that one expansion earlier, only certain terms will contribute to the sum. Here, it's the odd number terms here, okay? This is the odd number terms here. So the odd number derivatives, the odd number terms contribute. So how do we write an odd number? Writing an odd number is 2 times an integer plus 1, or 2 times an integer minus 1. So the general pattern is now this, okay? The general pattern is this. The 2k plus first derivative, okay, at 0 is, now we're going to use that same argument from before, okay? The odd number terms contribute, so that's 2k plus 1, all right? Now, when k is equal to, say, 0, I get the first derivative. When k is equal to 1, I get the third derivative. But the third derivative, which corresponds to k equals 1, gives me a minus. So I want the odd numbered k's to give me a minus sign. Okay, that should work out well here. And guess what? That's all we need there, minus 1 to the k. And now when we push to the general term, the 2k plus first derivative at 0 divided by the corresponding factorial, 2k plus 1 factorial, we get minus 1 to the k over 2k plus 1 factorial. And so now how do we get our Maclaurin series? Well, remember here, and I just realized I should have wrote these as g's, not f's here. Okay, so let's go ahead and fix that. Whoops. This is what happens at the end of the semester, right? So let's go ahead and fix those as G. So G, 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 G. Okay. Now we have G of 0, G prime at 0, G double prime, G triple prime, the fourth derivative, the 2k plus first derivative. All right, so remember that sine x was our helper function. That was to help us expand our original function. So we know how to expand G. Okay, let's go ahead and write it in this color here. So sine of x, which is our G, is expanded as follows near 0. We have the sum from n equals 0 to infinity of minus 1 to the n over 2n, let's not put a dot there, 2n plus 1 factorial times x to the 2n plus 1. Okay, only odd number terms count here. And so now how do we expand x cubed times sine x? Well, we just multiply both sides of this by x cubed, okay? So x cubed sine x, we'll have an x cubed outside the sum, as I mentioned earlier, n equals 0 to infinity, minus 1 to the n over 2n plus 1 factorial times x to the 2n plus 1. And because x cubed is independent of n, I can go ahead and shove that through. So what I get instead here, when I multiply the exponents here, 2n plus 1 plus 3 is 2n plus 4. And folks, that's your expansion. That's your expansion right there. Again, new series from old. Okay, we have these operational properties, sums of power series, products of functions, okay? That's how we handle this. And so now you see how to expand certain functions as Taylor series. We saw some really good examples. Now, why is this useful? A lot of stuff. Approximation, differential equations. That's a key thing of where these Taylor series are very useful. Differential equations, certain solvers. Okay, sometimes we may only want to approximate a difficult thing up to a certain accuracy. And we'll see how to do that in the next video. But as far as all the actual content goes, hey, you're basically done. We're going to get some bonus videos out here showing you some more applications. And I'll see you in the next one.